This question says, two identical cars are traveling down a straight road. The first car moves with the speed of u, while the second car moves with the speed of 3u. At any given point, both cars brake uniformly to come to a complete stop. If both cars stop in the same distance, determine the value of the ratio of F2 over F1, where these are the forces acting on the first and second car, respectively. So if we have car 1 here, and we have car 2 here, and car 2 is moving faster than car 1. So this has an initial velocity of u, this has an initial velocity of 3u. Both cars are going to come to rest at the red line. So their final velocity is going to be 0. And it said that they both moved a displacement or distance of s, or they moved through the same distance. So the idea is that both cars have energy kinetic at the beginning, and then they have 0 energy at the end. And what was happening is that there was a force acting in this direction to slow each car down. Now, if we think about this, if these are identical cars, right, let's look at first how their energies compare. So energy kinetic of 1 is simply going to be 1/2 mv squared, or in this case, our v would be our u, right, our initial velocity. For energy kinetic of 2, that's going to be 1/2 m3v squared, which is going to be 9, because we square that 3, 1/2 mv squared. So the kinetic energy of car 2 is 9 times as great the kinetic energy of car 1 because it's going 3 times as fast. And so we have to square that 3, and that's how we get the 9. So if we look at this, the idea is that there is work that is done on each car to bring it to rest. And the amount of work is equal to the amount of energy that it initially had. So for each of these scenarios, the energy kinetic minus the, or let's just say this, plus the work done external, right? That's done by friction, and that equals 0. At the end of our scenario, there is no energy, there's no potential or anything like that. So my setup for my equation is going to look like this. My work is going to be a negative value, and that's because my force is to the left and my displacement is to the right. So if we look at a car individually, okay, it would be a frictional force or some resistive force, which is pushing to the left, whereas my displacement is to the right. And our equation for work, which is going to be F times displacement cosine theta. And the idea is that the angle between these two, right? So if we draw our S up here, our angle between these two is 180 degrees. They're pointing in opposite directions. And so that makes the cosine of 180 -1. And so our work is a negative work. And that makes sense because we had initial energy and then our final energy is 0. So we lost energy due to the work done here. So if we set this up, what we have is we have we have our energy kinetic is going to equal force times displacement, right? We put a negative there, we add it over. So our energy is going to equal our work, which is force times displacement. And our force is going to equal our energy divided by our displacement for each scenario. So if we're trying to make this fraction of F2 over F1, right, F2 divided by F1, that's basically going to be 9 energy kinetic divided by S over energy kinetic divided by S. And so what's going to happen is my S's are going to cancel out. And essentially what we have is we have the energy kinetics are going to cancel out as well, but I'm just trying to show this. 9 energy kinetic for car 2 over energy kinetic. So because the car 2 has 9 times the energy, essentially what we're going to have is we're going to have 9 times the force because there's just a 1 right here. So that fraction that we would have would be 9/1 for the ratio of force 2 divided by force 1. So this question says a green ball of mass m falls from rest with an initial height of h. A red ball of mass m falls from rest of 2h. What is the ratio of their kinetic energy of the red ball to the kinetic energy of the green ball? Energy kinetic red over energy kinetic green when they are separate when they separately reach the ground. Our correct answer is going to be 2, and so let's prove why that makes sense. So we have a green ball and we have a red ball. So here's our, well, let's draw the ground first. So here's our ground. Okay, that's our height equals 0. We're going to have a green ball, and we'll draw it here. And we have a red ball, which is basically twice the height. So this has a height of h, and this has a height of 2h, and both of their masses are the same, right? Mass and mass. So it says, what is the ratio of their kinetic energy when the balls reach the ground? So if we think about what's going to happen, this has potential energy due to gravity. This also has potential energy due to gravity. When they reach the ground here and here, they are going to both have kinetic energy. So if we look at the green ball and the red ball, how would we write their equations of energy? We would have energy gravity, or energy potential due to gravity equals energy kinetic, and energy gravity potential due to gravity, sorry, I'm mixing those up, equals energy kinetic. So if we write that out, that's simply going to be mgh equals energy kinetic for my green ball, and it's going to be mg2h equals energy kinetic for my red ball. So if we see this, then essentially if energy kinetic is for the green, the red is going to have 2 energy kinetic because it starts from twice that height. So if we're looking at this ratio of energy kinetic red, so energy kinetic red divided by energy kinetic of the green, basically what we're going to get is we're going to get 2 energy kinetic divided by energy kinetic. Those cancel out, and we simply get a ratio of 2/1 or 2. So this question looks at a box of mass m is held on the top of an inclined plane of height h. Friction between the inclined plane and the box is negligible. The box slides down the plane until it reaches the ground level with the speed of v. Continue sliding along ground, which has a coefficient of friction mu, until it comes to a complete stop after a distance of s. Which of the following is the correct expression for the coefficient of friction? So let's look at this question. Here's our ramp. Here's our slides. We're going to have our box at the top of the ramp at some height h, right? So this is the height h right here. It's going to slide down the ramp until it gets here, and at this point, it's going to hit friction. And so because of that, it's going to come to rest here at the very end. So our final velocity is 0. Our initial velocity here, because it's held at rest at the top, is 0, but at the very bottom, it has some velocity v. And what we're trying to do is we're trying to look at what is the coefficient of friction during this portion of the motion. So let's first just zoom in on the box as it's moving, right? So as it's sliding across our friction, the forces that are going to be acting on the box are going to be the force of gravity down. We're going to have our reaction force, which is normal force, up, and then we're going to have a frictional force pointing to the left, even though we're moving to the right. On the ramp, we're going to have our force of gravity down, and our normal force is going to be perpendicular, and there's really no other forces because it says friction is negligible on that inclined plane. So let's look at how we could apply energy to this scenario. At the top, we're going to have energy potential due to gravity. At the bottom, that energy is going to turn completely into kinetic. And at the end, our energy is essentially 0. We've lost all that energy. And that's because during this portion of my motion, there is work being done by friction. it moved some distance s, and so we're going to have work there. So let's apply our s here, and if we understand this, this is going to be work which is going to be negative. It's going to be negative because our force is opposite our displacement. The angle between those is 180 degrees. So if we're trying to find the coefficient of friction, we first need to understand that the sum of the forces in the x direction are simply going to be my frictional force equals mass times acceleration. Remember, frictional force is going to be my coefficient of friction versus my, or multiplied by my normal force. And in this case, we know the normal force is going to be mass times gravity, because that's equal to, excuse me, that's equal to the normal force. So our coefficient of friction is going to equal my frictional force divided by my mass times gravity. And in order to continue to move forward with this question, I simply need to figure out how can I find what my frictional force is. So to do that, that's where we're going to apply the concepts of energy within this. So at the beginning, we have energy potential due to gravity. That converts into energy kinetic at the bottom. And that is all going to be, or excuse me, we're going to subtract the work done by friction, and that's going to equal 0 at the end, because there is no potential, there is no kinetic energy here at the end. So if we're looking at this, we're going to say energy potential due to gravity is going to equal my energy kinetic, which is going to equal the work done by friction. So we can apply our frictional work and our potential energy at the beginning and see how we can use that to find that frictional force. So my potential energy due to gravity is mgh. The work done by friction is going to be force of friction multiplied by s, by displacement. And so I need to solve for this force of friction. So to do that, I'm going to divide each side by s, and I would get that the force of friction is going to equal mgh divided by s. So now what I can do is I can simply plug this force of friction into this equation for my coefficient of dynamic friction and solve for mu. So my coefficient of friction is going to be mgh divided by s divided by mg. Looking at that, mg's cancel out, and so I'm left with simply h divided by s. So how high was the block on the ramp, and how far did the block slide after it hit that friction? So another way to write that, which might help people, would be mgh divided by s, and then instead of dividing by another number, we can simply multiply by the reciprocal, which would be 1 over mg. And so again, here we can see that mg's are going to cancel out, and the thing that I would be left with would simply be h over s. So this question says, an object is dropped from rest and hits the ground. Which graph shows the object's kinetic energy varies with height above the ground as it falls? So our best answer is going to be this one, and so let's talk about why. The height, right? So as the object is here, if this is our ground, the greater the height, if that's our maximum height, our kinetic energy is going to be 0. And then as that object falls, so as our height decreases, our kinetic energy should increase. Now, why is it a linear relationship? Well, because if we think about what did it have here, it had energy potential due to gravity, and then it converted into energy kinetic. So energy potential due to gravity equals energy kinetic. And if I were to write this out, that's mgh equals energy kinetic, because we don't need to solve for kinetic or velocity. We're just simply looking at how does the height relate to that, right? And what we see is that this is a linear relationship, that as if we were to simply solve for EK, right? And write this in terms of y equals mx plus b. We would write it in a way of EK equals mg times h plus 0. Well, actually, we don't need to worry about this 0. But essentially, we can rewrite this as my slope of my line is mass times gravity. And then my x variable is the height. So we can see that this would be a constant slope. This slope here would equal mass times gravity. And that energy kinetic is simply a linear relationship compared to height. So this question says, spring constant 55 newtons per meter is used to launch a wooden block up a rough slope. The block reaches a distance d along the slope before sliding back down. The block has a mass of 60 grams. The spring is compressed 5 centimeters from the point shown in the diagram. The coefficient of dynamic friction is mu d between the block and the slope is 0.61. Calculate the distance d. So a few things we need to do first is we're simply going to write some values in SI units. So 60 grams is going to be 0.60 kilograms. Sorry, 0.0. So that's 0.060 kilograms. 5 centimeters is going to be 0.05 meters. And everything else looks good. Coefficient of dynamic friction is unitless, and then spring constant K is in 55 newtons per meter. So looking at this, we have the spring compressed. So what we have here is we have energy potential due to the spring. That spring is going to launch it upwards, giving it potential energy, and then eventually it's going to stop here. So we have to think about, as it's moving upwards, what are the forces that are going to be acting? So there's going to be the force of gravity. We're going to break that force into its two components, both its parallel and its perpendicular. And the parallel component is pushing down the ramp, so that's slowing it down. We have our normal force acting on the block, and we're also going to have friction, right, up a rough slope. So we're going to have a frictional force, which is pointing down the ramp as well. So looking at the sum of the forces, and we'll call that the x direction, and we'll just say, for the sake of the motion, that up the ramp is the positive direction. So that's going to be minus the force parallel minus the force of friction equals mass times acceleration. So we see that both of these forces are combining to reduce the energy of the wooden block. And if we look at this, we're trying to find D, right? So the idea is the energy that we have initially is all potential. We're going to have some energy here at the top, which is going to be due to gravity. And we have, these are not going to equal each other because we have work done on the system, not only by gravity, right, but also by friction. If it was just gravity, these two would be equal. However, with friction involved as well, this should be less than this. So our equation we're going to write is energy potential due to the spring minus the work done by friction, because that's my external force, is going to equal the energy potential due to gravity. And again, we're trying to solve for this idea of D. Now, as we're going through this question, right, this is simply going to be 1/2 kx squared minus the force of friction times the distance up the ramp equals mass times gravity times height. So if we look at this question, we know k, that's given here. We know x, that's given here. Distance is what we're solving for. The force of friction we can solve for. Mass we know, gravity we know, and height we can solve for. So here's how we're going to do that, right? One thing is if we look at our ramp, and if the block ends here, and we know this angle is 35, and we know this distance here up the ramp, then we can say if this is distance here and this is h here, how would I solve for that? So that is my sine function, which is going to provide that, right? So the sine of theta is going to be opposite, which is h divided by my hypotenuse, which is d. So h is simply going to be d sine theta. So I can plug that in to there, right? Everything else we know, k, x, we're trying to solve for d, mg, we just replaced h with d as well. And really what we need is we need our force of friction. So understanding what force of friction is that the force of friction is going to be mu times my reaction force, which in this case is my normal force. My normal force is going to be equal to my force perpendicular, and my force perpendicular is essentially going to be this component here of gravity. So that's force of gravity times the cosine of theta. So I can plug that into this part of my equation. And let's see what that gives us. So we get 1/2 kx squared equals, minus, force of gravity is mass times gravity, cosine of theta times d equals mg sine of theta times d. So we just plugged in those two equations into that. And essentially what we're trying to do is we're trying to isolate d, right? Get d on one side and find what that is. So what I'm going to do is I'm going to add this section over to the other side. And we would get 1/2 kx squared, and we'll talk about why this makes sense, equals mg d sine theta plus mg d cosine theta. And essentially what this is, right, mg d sine theta, that is the energy potential due to gravity, and this is the work done, right? So the initial spring energy equals whatever gravitational energy I have at the end, plus the work that I lost due to friction. And so what we're going to do is we're just going to pull out our d value here and say this is 1/2 kx squared equals d times, and I'm also going to pull out mg. So this is mg times the sine of theta plus the cosine of theta. It's a lot of algebra with this one, but once we get it set up, right, it's just algebra working through this. And we're going to get d by itself, so we're going to divide each side by mg sine plus cosine theta. So d equals 1/2 kx squared divided by mg times the sine of theta plus the cosine theta. And all of that is going to give us a distance which is around 11 centimeters or 0.11 meters. And we plug our values in.